Hi, I'm Sorani from Posttech in South Korea. I'm going to talk about our work, FIFO, Learning Fog-invariant Features for Foggy Segmentation. Semantic segmentation has great advantages, but they only focus on improving accuracy under clear weather, so they have performance degradation on a foggy scene. However, for real-world application, robust recognition on foggy scene is very crucial. So, this task aims to improve performance on both foggy and clear weather. For foggy scene segmentation, training datasets are categorized into three domains as clear weather, synthetic fog, and real fog. Synthetic fog is a dataset applied with realistic fog effect on clear weather, so it has the same content with clear weather. Real fog is unlabeled foggy scene dataset. Existing methods tackle this problem by the curriculum domain adaptation that gradually adapts a model from light to dense fog. They have achieved impressive robustness, but they demand heuristic modules and leads to performance degradation in clear weather. Unlike them, FIFO does not need to control fog density in training. Also, FIFO clearly improves performance on both foggy and clear weather. To design FIFO, we consider fog conditions as neural styles, but existing style representations like ground matrices are not desirable for our task since they are affected by other factors like content. In the slide, two images have the same fog condition, but their ground matrices are not exactly the same. To address this issue, we designed fog path filtering modules that extract only a fog-relevant information from the style in the form of fog factors. FIFO Framework consists of two steps to update the fog path filter and segmentation network. By alternately optimizing the fog path filter and segmentation network, FIFO reads to fog-invariant features of the segmentation network. In the first step, we train the fog path filtering module with freezing weights of the segmentation network. The fog path filtering module takes the ground matrix as input and extracts fog factors. In the rows, fog factors from the different fog domains are far from each other, and those from the same fog domains are grouped closely together. Then, we train the segmentation network with freezing fog path filters. With the segmentation loss, the fog style matching loss reduces the gap between fog factors from different domains for learning fog-invariant features. Also, the prediction consistency loss forces the consistency between clear weather and synthetic fog. To investigate the impact of FIFO on fog invariance learning, we first demonstrate that FIFO effectively reduces the gap between fog domains in the space of fog vectors. We also qualitatively verify the impact of FIFO. In specific, we reconstruct images from features of the segmentation network trained by FIFO. The results demonstrate that FIFO allows to sharpen images effectively, while emphasize boundaries. The efficacy of FIFO is demonstrated on real fog and clear weather datasets. As shown in the table, our method substantially outperforms previous work on our datasets. FIFO also qualitatively improves segmentation results in real foggy images and recognize objects robustly even in dense fog. Finally, we investigate the generalization ability of FIFO to other weather conditions. As shown in the figure and table, FIFO can be generalized to rain and frost weathers. Thank you for attention. For more information, please visit our poster session.